All right, so this is homework 3, part B. We're going to be looking at the Nusselt number with laminar flow over a flat plate. Right. So in the x direction, the Nusselt number is 0.332. That's not 332. 332 times the Reynolds number to the 1/2 times the Prandtl number to the 1/3. So what does this mean, right? Well, the Nusselt number is a ratio of the conductive heat transfer, or the convective heat transfer over the conductive heat transfer, right? And so when we're looking at a flat plate, we can draw out our flat plate here. And we're looking at the flow, right? So heat's coming in here, right? And when we hit this boundary here, we create a boundary layer, right? That has some length, right? So we'll say in this, it's x, right? And some distance between, right? Which is delta, right? When we look at this, we can use this, right? Where the Nusselt number is the convective heat transfer over the conductive heat transfer, right? And so we know, right? We know both of these values, right? So this is just hx, right? Over k, right? That's our convective over our conductive, right? So our goal here is we want to maximize h, right? So what is h, right? This is h, right? That's our convective heat transfer going in, right? We want to maximize that. Now, how do we do that? So we're going to break down this initial equation here. I don't know why there's a point here, right? So we have our nu. This is a u. Now we can look at our Reynolds number. Well, our Reynolds number, that's our dimensionless number. And we know that to be our velocity times our density times some length, right? And so here it's going to be x, and that's all over our viscosity, right? That is our Reynolds number. It's a dimensionless number. It's very famous. And for laminar, it's a very important, right? And so next we'll look at our Prandtl number, right? So what is our Prandtl number? It is our momentum diffusivity over our thermal diffusivity. Right. So our thermal diffusivity, we have done this in our other videos, right? It's going to be our K over Cp, K over Cp times our rho, right? And then we have our momentum diffusivity, which we did in, I believe it was homework 1, part A, right? We looked at it. And that was our viscosity divided by our density, right? So we can simplify this down, and we will get our viscosity times our heat capacity over our K, right? So our Prandtl number equals, right, this term here of viscosity times heat capacity over our thermal diffusivity, right? And so now what we're going to do is we're going to use this to simplify our initial equation, right? So we have this nu, right? Well, we just found nu up here. That's going to be hx over k equals the 0.332 times our Reynolds number, our v rho x over mu to the 1/2 times our Prandtl number, our mu Cp over K to the 1/3. Now, earlier I said that we wanted to maximize H. So now what we want to do is we want to get H by itself. So when we do that, we get H equals 0.332, and that 332 is an experimental value that was determined for this specifically. So it is not a number I just made up. Times our V rho x over mu to the 1/2 times our density times our heat capacity over K to the 1/3 times our K over X, right? So we can further simplify, right? This is just K to the 1/3. This is K to the 3/3. That can be simplified. This same thing with X here and this X here. So when we do that, we get H equals 0.332 times our velocity to the 1/2 times our rho to the 1/2 over our mu to the 1/2. And then when we do it with the x becomes negative, right? So we're going to pull that out. And so here we get our mu Cp both to the 1/3 times our what is now K to the 2/3 over X to the 1/2. And so when we look at this, what do we notice, right? Well, what I see is we have our X in the denominator here, meaning when we increase X, our heat transfer, right, which is what we're trying to maximize, is going to decrease, right? So when we increase this value, when we're further away, when we make the X larger, our heat transfer is going to end up being smaller. And because of that, that shows that we want this surface here to be perpendicular, right? We want our flow to be perpendicular in order to maximize heat transfer, because we don't want this long X value. That would then decrease our overall heat transfer. So that is how we use the Nusselt number to to maximize heat transfer in laminar flow over a solid plate.